Hello, I'm Dr. Jan Kupec. I'm a Technical Director for Ground Engineering at Aurecon in Christchurch, New Zealand. This is a presentation about the 2015 Nepal earthquake and its aftershock, specifically focusing on geoscience aspects. It's one of many presentations. Here are my co-presenters as well. So again, limiting myself to geotechnical aspects. When we arrived as part of the EERI team in the country, what we actually discovered that there was a relatively good reconnaissance on the Kathmandu and surrounding districts, but rural areas were difficult to access itself. The GEA team, B1, which was in the country, were providing us with very useful information along with the Japanese colleagues, and out of the collaboration, we decided that we actually want to focus on the impact of geohazards on lifelines and building outside the Kathmandu Valley, which this presentation is about. The main issues in Nepal were around liquefaction, lateral spreading in the Kathmandu Valley itself that caused foundation distress. Out in the rural areas, more hilly terrain, we noted ridge amplification effects followed with strong shaking that caused building damage. In line with strong seismic shaking, rock and soil mass failures were observed on numerous instances as well. Looking at the shaking intensity from the main event, which is the left-hand side picture, in the aftershock itself, the aftershock seemed to have released much lower amount of energies as one would expect. However, the seismic shaking that was not the sole instance of damage, which the aftershock map actually shows. There's a distinct cluster around the eastern part of Kathmandu, where a large number of aftershocks actually has occurred. The main event and the aftershock on the 12th of May, the aftershock itself occurred in what is called a seismic gap between the 1934 earthquake and the 25th of April 2015 earthquake. The strong clustering in that area caused some damage to slopes, and repeated shaking obviously damaged unreinforced masonry structures fairly severely. If you're looking at slope stability modeling itself, that was available at that time. This instance is showing the University of Michigan for both main event and the aftershock. Shows that the majority of the slope stability is focused around in the eastern areas of the aftershock itself. Different view of slope stability by the Earthquakes Without Borders with the Durham University shows again strong clustering around the aftershock area, especially around the Sindipalchok and Kolkata area. And that caused the selection of the sites predominantly around the Charikot and Chautara townships itself. What we noted following the visits to these districts is the predicted and observed land damage correlated very well. We can compare slope instability with building damage, especially in steep terrains such as Nepal, and the US aid map for humanitarian assistance correlates very well with the predicted damage for slope instabilities. Looking at foundation performance itself, some foundation failures were observed in the Kathmandu Valley itself. They generally related to poor ground performance under seismic conditions such as lateral spreading and liquefaction-induced weakening of the soils that caused traditional soil-bearing capacity failures. Foundations in rural areas were often on steep terrain, geotechnically slightly more competent, and when we, however, surveyed about 150 buildings in Chautara, it became fairly apparent that the buildings sitting on steep or inclined terrain performed worse than the counterpart sitting on level ground. Traditional masonry, unreinforced masonry superstructures that many instances not perform as well as the foundation systems they were sitting on. Many modern RC frame buildings that were damaged and were tilting. Many instances they observed a poor concrete frame detailing below the ground floor caused issues. It created short columns, and quite often the continuous strip foundation that should have been installed were lacking. Rebuilding, where it was observed very shortly after the earthquake itself, employ the same foundation systems, namely shallow foundations. Picture on the right-hand side shows a typical structure sitting in the more rural area in a mid-sized town. Looking at foundations, especially the non-engineered traditional versions, the picture on the left-hand side shows traditional Nepalese townhouse, where the lower structure is comprising of timber, columns and beams with reinforced masonry, sometimes even mud stone masonry directly above it with relatively sturdy frames. The cutout shows the stone plinth on which the column itself sits. Looking at the stone plinth themselves, there is actually a protrusion in them that's about 1 inch or 25 millimeter high and 2 by 2 inches or 50 millimeters square. And the matching column has actually a divot, and that way they actually are interlocking, preventing the column itself from being kicked out. The plinth itself in many instances was observed to sit on either directly rock itself or geotechnical competent ground. Looking at how these foundations actually performed, not too bad overall, consider the severe degree of lean under the 3-story masonry structure, and the only distress can be actually seen in a vertical split in the main column, but generally speaking they performed quite well. More modern foundation types on the left hand side, a typical detail. They're constructed by creating a trench, filling those trenches with flat stones, putting lean concrete on top of that to level it off, and then creating a plinth out of concrete and connecting that to the superstructure itself. The ground around the plinth is quite often backfilled by hand, and the gap between the ground and the first floor or 4th story is actually backfilled with either stone and mud infill or unreinforced masonry backfill. How do these foundations perform? One sees an example on the left-hand side. In this particular instance, the poor quality of foundation concrete is evident. What we have also noticed is the continued vertical steel reinforcement, and that creates generally an issue around the interaction between the foundation and the superstructure itself. On the right-hand side, a relatively massive foundation is not necessarily helping because the stone infill failed out of plane, and this foundation element itself worked its way at loose, especially because the neighboring side actually failed itself. More at foundation failures, we're looking at shallow foundations overturning, as shown on the left-hand side. But we also looked at crushing failures where the concrete lacked reinforcement and quality, crushed itself, the out-of-plane failure of the stone reinforcement in this particular instance, the entire structure, which is a radiator tower on top of it, tilted, hit the small white building in the middle, and then pushed that white building into the adjacent 3-story RC frame, affecting damaging that one as well. But we also saw where construction was relatively good on the foundations itself. The building moved excessively and caused a tensile failure of the reinforcement itself. One particular aspect that we noted in the steep terrain is where the construction was such that the foundation systems were built and the first part of the frame was built, and the ground was then compacted behind the unreinforced masonry infill and relatively poorly so using hand compaction only. During the seismic shaking and especially the ridge amplification, that soil wedge was accelerated out of plane, damaged the columns and the frame itself and caused a collapse. Picture on the left hand side shows Erku townhouse of 7 stories collapsed down the slope. Picture over here shows a snapshot I took from a poster showing best practice, where pad foundations they're well tied together with cement infill mortar being used, and that actually is a guideline. What, however, is not shown how to build buildings in steeper terrain. Most of the guideline is limited to flat terrain. Neither is actually given any guidelines for ridge amplification. Ridge amplification was a large topic. It was very notable that houses along steep ridgelines were more damaged than similar buildings away from ridgelines. 100 meters difference was significant. The effect was very notable in Chatara and Charikot, where buildings leaning in one particular direction and out of plane failure was also noted in one particular direction. So there's a strong suggestion that ridge amplification is observable in these areas. Looking at geohazards, Nepal is very mountainous. The terrain is very, very steep and prone to geohazards. The typical land slippage and rockfall impacts were numerous. 2 examples I chose, the Tamakoshi River later and the Helang Belang cliff collapse site. The main picture shows a view from across the valley using telephoto lens. We were informed by the municipal engineer that the landslide buried a village, and in the central area of the picture one see remnants of the village itself, and the relocated temporary villages in the far left-hand side of the picture located in the ridge spur itself. What actually happened over there? There's a 300-meter cliff top and 200-meter very steep near vertical runout slope. The orange triangle shows the view from the ridge top down. What was noticeable that this one, according to Vance, was actually a rock topple area, which is a common engineering geology classification. There were several meters of cliff edge lost, and the debris inundated part of the steep terrain at the base. We also saw historic boulders at far bottom, and I'm going to be talking more about this in the next couple of slides. Looking at what happened at the cliff top, when we arrived, the over-enthusiastic drivers parked very close to the cliff edge, so we asked them kindly to reverse to the side that was relatively undamaged. We were able to trace cracks along the entire cliff edge that were running sub-parallel, cracks from hairline to about 75 millimeter wide. We're running within and deep into the ground itself, and we're about 15 to 25 meters setback from the cliff edge. And the damage was very similar to other seismically triggered rock topple areas. Looking at the current runout areas in red dashed, that's where the majority of the current debris stopped, but historic boulders showing further, much further down slope, which indicates that there may have been events in the past that exceeded the current damage to the cliff itself. Fortunately, the village that was buried underneath it was relocated to a spur far away from the current debris runout in a relatively safer area. How can we actually be sure that is the case? Well, we use tools like the Fabersham angle, or referred to sometimes angle of reach, or shadow angle approaches, which are based about 100 years back on work in the Austrian Alps. These tools work very well with simple clinometers or smartphones, and a very good publication that summarizes various mechanisms for rapid assessments is by Hunger from the University of British Columbia. Rock mass failures. It's another large topic. I picked over the site over here, northeast from Singati, along the Ganga Road. On the right-hand side is the picture from before, and directly underneath is the picture directly after the event. One can see the large amount of debris deposited in the road itself, which in many places is actually oversteep. The retaining walls along this road itself were extensively damaged. On this picture, there's about 450 tons of debris sitting on Gabion wall, and the Gabion wall in the bottom third is extensively bulging out. So even removing the debris itself will not necessarily solve the problem in this particular instance, as the area is already damaged, and that is all pre-monsoon rain. So irrigating this particular area might cause further damage. If you're looking at roads itself, not just the Tamakoshi area, they are often blocked for hundreds of meters by significant landslides. It will take a major engineering effort to clear these roads, but it will also pose an ongoing life safety and maintenance issues. These slopes are unrealistic to be remediated. They are often hundreds of meters steep. They are very, very prone for ongoing reactivation, especially due to monsoon rains, and it will likely to continue to be active for several seasons. So if I want to sum up my findings, we saw limited geotechnical damage in the Kathmandu Valley itself, but it was observed it could have been either directly related to the underlying geology or the building phenology. We have observed that shallow foundations are relatively common, and if built well, they perform well. However, in the rural areas, often the superstructure failed, not necessarily the foundations. We have seen that geohazards have impacted buildings and infrastructure, with potentially one exception, which were bridges, which appear to have had a relatively high level of resilience. Rockfalls and land slippage are likely to get worse during the wet season, and there's a high likelihood of reactivation of older landslides. The effects will be felt for many years to come, not just one seasonal cycle. And probably a question to be asked is whether ridge amplification will be considered in the rebuild. There's more information and reports, data, and photos on the EERI Virtual Clearinghouse website that I would like to draw to. And lastly, I would like to acknowledge that I went there not by my own, but as part of a large team, and there were many people behind the scenes that have contributed to the successful mission. Thank you very much.